Hello, everybody. Welcome to this seminar. My name is Kukacka, and I prepared a talk about the Flickermeter, a need for an update. First, of course, I will tell you what is Flickr and what is the Flickermeter about. How does it work? Then I will talk about the problems with the current standard Flickermeter, and I will show you a few proposed updates to the Flickermeter. And then I will also present a fragment of work which we did on comparing two Flickermeters, an update with the standard one. This is not meant to, so if you are an expert on Flickr, I don't know if there will be something new for you. So on the other hand, if you are not, then I hope that the outcome of this presentation will help you understand the problem of Flickr and especially the Flickermeter. So let me start with the definition of Flickr. What is Flickr? We have a public grid, and we talk about Flickr when we connect some time varying load to the grid. This load can either be a small appliance like a cooker or microwave, but it can also be some large facility like a factory, for example. And when you have the voltage grid, which can be modeled as an ideal voltage source and an impedance. This impedance in reality is caused by cable impedance, overhead lines, and also transformers and all network components that are in the path from the plant to the point of connection. And the point is that when you have time varying load, you switch on a cooker, for example, or the factory. There is some harmonic generating device. You will produce a voltage drop over the network impedance, and this will cause the voltage at the point of connection to fluctuate. And if you use the same voltage to supply a lamp, then there is a risk that the lamp will fluctuate too, and the output of the lamp, the light, will not be stable. And if these instabilities happen at certain frequencies, or it's just a singular voltage drops and events, then there is a risk that you will see the light flickering, and it will disturb you and may cause headache. So this is what we describe as flicker. We talk about visible flicker. Okay, sometimes when you Google up flicker, you can find some stroboscopic effects, phantom array effects, which are related to high frequency phenomena. But this is we are discussing flicker, visible flicker under static conditions. So the case where you can see actually that the lamp is fluctuating. Okay. For having the flicker under control, we have this standard Flickermeter, which is described in an IEC standard 61000-4-15. And it is a complex algorithm where the input is the voltage measured from the grid. And the algorithm is separated into 5 different blocks. In my slide, we will go, I prepared a short example, and we will go block by block what happens to the signal. So basically, you have the model of an incandescent lamp in the Flickermeter, inherently in the design, and also a model of a human observer. Yes. So at this moment, let us have a look at what happens to the signal in each specific blocks, how the lamp is modeled, how the observer is modeled. The Flickermeter was developed in 1970s and published first time in early 1980s. At that time, incandescent lamp was very common, and it was natural to choose the incandescent lamp as a reference lamp. So the lamp that is being modeled is 60-watt incandescent lamp with 2 filaments. Yes, okay. So I prepared a simple example. So this is a zoom on a modulated voltage. The blue shape is actually a signal of the voltage at 50 Hertz, and you can see that it is modulated very slowly. So this is one change per minute. So it's 1/120 Hertz, and the modulation level is quite high, and this is one of the signals that is used to calibrate the Flickermeter, because this particular signal should result in PST1, and the output quantity should be just the limit of visibility of the flicker. First we have the block 1 in the Flickermeter. This is just a normalization with respect to the RMS value. So the idea is that you calculate RMS value of the voltage every 10 milliseconds in case of 50 Hertz systems, or every half cycle. And then you filter those RMS values with a filter with a time constant 27.3 seconds. And then you divide the original signal with this filtered RMS values. So the total RMS value should be close to 1. In case of very slow fluctuations, you see that the filter accommodates to the new RMS value between the switches. That's going to be imported later on. Then there is block 2. Block 2 is already a part of the model of the incandescent lamp. So you know that the incandescent lamp is resistive load, and when you want to calculate the instantaneous power from voltage, you just calculate the square.
Just can you maybe put your screen, share your screen on the Zoom so that we can see better the PowerPoint?
Oh, I did not. Okay, sure.
This is mostly updated.
Sure. So let me share the screen.
If you have the right. I think it's better.
Is it better now? Oh, okay, perfect. Thank you for pointing that out. Okay. So as I was saying, you square the voltage. By this, you obtain a signal that is proportional to the instantaneous power. In the Flickermeter, there is one common scaling constant, so don't worry about the scaling. It's just about the shape of the signal. There is one big common scaling factor at the end of the algorithm. So squaring in block 2, we obtain the instantaneous power. And then there is block 3, which is a bank of filters. 2 of the filters are just to limit the bandwidth of the signal. There is a high pass filter, first order, a very slow one, which is basically to remove the DC component of the squared voltage. Then there is a low pass filter, 6th order, and the aim of this filter is to kill the fundamental voltage. So when you have 50 Hertz voltage on the grid, you square it, you obtain 100 Hertz. So this is to kill the 100 Hertz component, because and all other high frequency components as well, because they don't contribute to visible flicker, at least with incandescent lamps. For 50 Hertz systems, the cutoff frequency is 35 Hertz. It's 42 Hertz for 60 Hertz systems. And then we have a very special filter. It's a weighting filter. And this filter was designed after a series of experiments done since 1950s already. And its aim is to mimic the response of the incandescent lamp, the frequency response of the incandescent lamp, and also of human eye and of the retina. There are a few misconceptions about this filter. So the original research it was based on was published in 1950s, and it was done with green light and with only 2 degrees of observational target. That doesn't mean that the data that this filter is based on are from this experiment. Only the idea is based on this experiment. The experiment went like the human observers were presented with a flickering light at a given frequency, and they were interested in the modulation magnitude, the threshold magnitude at which they start perceiving flicker. So you have like several points of the magnitude response of the filter. And then it was interesting to find out back then that the filter, from this magnitude response, you can create a filter if it's a minimal phase system. So you can see the impulse response of the filter. The transfer function has this shape. In the standard, you can look up all the parameters. I did not bother to put them here. I think that wouldn't be too much interesting for you. So this is the output of the weighting filter. Still, it is just a filtered signal of the luminous flux. So the assumption is that with incandescent lamp, the instantaneous power is proportional to the luminous flux produced by the incandescent lamp. And there are also a few simplifications in the Flickermeter. It's a linear system. It's simplified around some operating point. When this weighting function was developed, they did experiments not with green light, but already with an incandescent lamp in office-like conditions. And the filter corresponds to perceiving flicker under these office conditions. So this is one of the misconceptions. Sometimes you can read that this filter is based on green light. It's not. It's based on incandescent lamp, and it inherently contains a response of the incandescent lamp. Okay, I think we can go further. So this is output of the block 3. Then we have block 4. Input of the block 4 is the filtered signal from the luminous flux, somehow referring to the visibility, but it's still not the flicker quantity itself. Block 4 is based on another body of research done in 1970s. What they did back then was present the observer with a steady light, and then there was a small pulse at one time, followed by another pulse in a very fast sequence, very short interval. But the interval was varied, and they found a threshold at which the observers start seeing 2 different pulses. And the pulses could be positive or negative because there was a steady light level. So if it was a drop, it was a negative pulse. If it was an increase of the luminance, it was a positive pulse. And what they found out was that the sign of the 2 consecutive stimuli was not important, so that you can square the signal to get rid of the sign of the pulses, of the light pulses. And then also that the order of the 2 consecutive stimuli was also not important. So you could calculate an integral over some time, or in case of the Flickermeter, this is approximated by another filter with a time constant of 300 milliseconds. And after applying the big scaling constant that I told you earlier, we obtain a quantity which is called instantaneous flicker. You can see in our little example, you can see the instantaneous flicker. Now it is interesting to see. Here I put the initial voltage waveform just for comparison, and you can see here that the peak and the instantaneous flicker is higher than the other two. This is because, as I told you earlier, in block 1, this is because of the normalization, because the changes in the voltage are too far away. It's 1 minute between the changes. So the filter in block 1 adapts to the new RMS value. And so this voltage change, they are the same, but this one happens with respect to smaller RMS value. So its relative size is higher. On the other hand, the downwards slope is done with respect to a higher RMS value. So its relative size is a little bit smaller. So this is why you can observe different size of the peaks in the instantaneous flicker. And the output quantity is scaled so that the value of 1 is the visibility threshold of flicker. And as I said, the Flickermeter is linear, so the double the voltage modulation at the input results in doubling the flicker quantity. And then after block 4, we can move on to block 5, which is also a very interesting signal processing algorithm. So the instantaneous flicker is a continuous quantity or sampled quantity, but for every sample of voltage, you get one sample of instantaneous flicker. But the final quantity, called PST or short-term flicker, is evaluated once per 10 minutes from the instantaneous flicker. In fact, the 10 minutes can be changed to some other value, but 10 minutes is the most common value. The standard allows, I think, as short as 1 minute, but also faster. But in voltage quality and power quality measurement campaigns, you will always find 10 minutes. Well, this value was chosen just so that it would cover small, very fast changes, and the slow changes would be like 2 hours phenomena would be covered by multiple PST values. So it's a compromise between being too short intervals and too long intervals. So what happens in the block 5 is that you take the whole signal from the instantaneous flicker for the 10 minutes, and you sort the values, and you have a look at the percentiles. This is what we obtained for our example, and I denoted the percentiles with yellow circles. I hope they are well visible on the screen. When they were designing the block 5 in the 1970s and 80s, they had to look at some data coming from arc furnaces, because back then arc furnaces were the largest contributors to flicker. So they took they had to look at this data, and they noted which quantiles would be interesting to observe. So that I noted the quantiles here. You can see that they are not linearly distant from each other, and then there is a weight associated with each quantile, and these weights were chosen so that they had a few signals which they knew that the PST should be 1, and they had the quantiles, so they ran an algorithm to determine the weights, and then you perform a sum and a square root, and you obtain the PST. And the PST is the most important index for the Flickermeter. It's the main output from the algorithm. And then there is also a long-term flicker. It's rather useful not for the light itself, but rather for monitoring the power quality. So it's calculated over 2 hours interval from the PST values using this third order formula. Again, it's rather a compromise, and it's rather focused on monitoring the voltage quality over long periods of time. Okay, so that does it for for the Flickermeter. We went through the 5 blocks. You already know what happens after each block. And here I listed a few issues with the Flickermeter. Many of them are well known, well recognized, and for many years people have been working ideas how to fix them. And nonetheless, they must be mentioned here. So already, I think since 1990s, there were observed discrepancies between the reported flicker values of the PSD and PLD and the number of customer complaints on Flickr. So there were, in available literature, people discussed if the block 5 is well defined. I will show you later on that there was some additional body of research indicating that the block 5 might not be correct. But then, is it truly expected that the amount of complaints should be proportional to the measured PSD values? Because when people complain on Flickr, nobody asks them what kind of lamp do they use. There are many variables at play that are not under control. The weariness of the people, do they come very in the evening from work, they are tired maybe, so the perception of Flickr is different. Use different lamp or use fluorescent lamps maybe in the 1990s, but today many people use LEDs, and this is a completely different story. I will come to back later again. So I'm not sure if, personally, I'm not sure if the number of customer complaints on Flickr is a good way to judge on the quality of the PSD metric. The second issue is that, well, I already mentioned that the incandescent lamps are not in use anymore. They have been phased out since many years, and they've been replaced by CFLs and LEDs. So that means that the block 2 is obsolete, and it needs to be replaced by a more complex algorithm to model the behavior of LED lamps or CFL lamps. And then also block 3, the weighing function of the block 3 was done on incandescent lamps, and with the spectrum of distribution of the light was that of incandescent lamp too. But LEDs have a different spectrum. You can have cool white LEDs, neutral white, warm white LEDs. So that might also play a role with Flickr. The weighting function of the block 3 might need to get adapted too. Then what changed in the 1970s and 80s is the grid equipment, both on supply and customer side. We have distributed sources, photovoltaics, wind farms, and on the consumer side, we have switched electronics. The big facilities that they used to create a lot of Flickr now are bound by the standards to not produce that much Flickr. They use power factor correction techniques, which cost them a lot of money, of course. They use voltage conditioners to fix the current consumption, not to create too much voltage distortion. And as a consequence, the very common disturbance patterns that might cause Flickr are not the same as they were in the 1970s. So maybe it is also time to revise the block 5, which was based on arc furnace data. This might be a bit very too specific data set to revise the block 5. It may prove that it does not play a role. I don't know. We need research on that, but it may prove that the block 5 might need some revision too. And then when we have a nice working Flickermeter, it might be a good idea also to extend its usage not only to office lighting conditions, but also to other purposes like public lighting. That would mean adapting block 3, 4, and 5 to mesopic vision, which is very different from photopic vision. Usually the response of human eye, Flickr, the human eye is less sensitive to Flickr, So for public lighting, maybe this could mean that we could relax the standards, limiting the flicker, which could save some money probably on power factor correction. I don't know. And then we also have other flicker-related artifacts, not only visible flicker, but LEDs by themselves may also produce stroboscopic effects, high-frequency phenomena, and these are not reflected by the Flickermeter at all. This is important to have in mind. So in future, it's just my idea. I think that it would be interesting to construct something like similar to the Flickermeter, but with focus on the stroboscopic effect, for example. So the idea how to fix the discrepancy between incandescent lamps and LEDs was to split the part of the lamp and of the human observer. As a result of this effort was the Luminance Flickermeter, which is now standardized. IEC technical report 61547-1. So it's a very similar algorithm. Only the model of the incandescent lamp was taken out. So you can see that the block 2 is missing. It was the squaring which converted voltage to instantaneous power. The input of the algorithm is not voltage anymore, but it's the luminous flux. That means that you either measure the luminous flux itself, or you have some lamp model, an extra lamp model that you use to convert voltage to luminous flux, and then you apply this Flickermeter. The second change in this Luminance Flickermeter with respect to the voltage-based one is the weighting function in the block 3. So what they did in this research was to remove the effect of the incandescent lamp, the frequency response. So they identified the frequency response of the incandescent lamp filament as a second order system, and they simply divided it out from the original weighting function. So I use this plot here, so you can see the blue line is the original weighting function, which includes also the incandescent lamp response. And then there is the red one where already the incandescent lamp is not accounted for. But that's for the frequency response, right? But the human observer was still, when acquiring data during the experiment for designing this function, the human observers were still exposed to light coming from incandescent lamp. That means the spectrum was a black body radiation at some 3000 kelvins probably, and at the office lighting conditions. So it means that under different conditions, this function might not be relevant anymore. Well, it's a simplification after all. So we have to do with something. Then the block 4 and block 5 remain the same. They are the same, and the PST and the PInst are comparable with the voltage-based Flickermeter output. So if you have an incandescent lamp, 60-watt incandescent lamp, you should be able to receive the same PST value from the same voltage waveform. Okay. So now that we have a way to evaluate the PST from the luminous flux, not just from the voltage, the luminous Flickermeter can be used to compare lamps between themselves. This is just to illustrate the difference between the lamps. To the left is a PST generated by incandescent lamp as a result from sinusoidal modulation of the supply voltage. And you can see that the incandescent lamp is able to produce visible flicker up to 100 Hertz, and that the most relevant frequencies for the flicker are the interharmonics. On the other hand, the same experiment but different lamp. This was an LED, and you can see that LED is able to produce visible flicker with interharmonic frequencies at the supply voltage up to 1 kilohertz or maybe even above. This is due to the driver, and these responses will be very different if you use a different driver for the LED. That's a different story, and a lot of other research going in this direction too. So this is just to illustrate what difficulties we have to face if we want to develop a LED lamp model, and that also different frequencies need to be taken into account, not just up to 100 Hz, but also beyond 100 Hz. These frequencies will be relevant for visible flicker with LEDs, or are relevant. So the Luminous Flickermeter addresses a lot of issues, mainly with the incandescent lamp, which is removed from the algorithm, but still it has some drawbacks too. So as I said, the block 3 is still based on observers that are exposed to incandescent lamp. The spectrum of distribution is that incandescent lamp. At luminance level, relevant for office work. And block 5 is still optimized to waveforms produced by incandescent lamps disturbed by arc furnaces. So if we have different disturbance patterns in the grid, then still the block 5 possibly, I don't know, I'm not claiming this, but possibly it might need to be revised. And still it only accounts for visible flicker, no stroboscopic effect and phantom array effect, etc. Because these frequencies will still be filtered out in the block 3. And also the block 5 is not built to respond to those phenomena. Okay, so this was introduction into the Flickermeter. So remember that we have two of them. One is voltage based and the other is luminance based. And this is one of the proposed updates to the voltage based Flickermeter. It was published in 2014, and it was designed to address the discrepancy between the number of customer complaints and the observed PST values. And based on research published in 1915, the authors of the update proposed that the block 5 might be replaced. You remember the complex statistical evaluation with the quantiles. So they think that it could be replaced by simply calculating RMS value of the signal based on this research by Mr. Ayre. When they try to calculate this value, they notice that for very low frequencies the response is too small, so they added the compensating filter, and they also removed the high pass filter to fix for the lower frequencies. Me and my colleagues from the Technical University in Dresden and Brno University in Technology spent some time comparing this proposed update with the standard Flickermeter, the original one. This is because this update was is being seriously taken into account in the working group for the IEC standard, and they are considering, or they have been considering in the recent years that this might become the new standard Flickermeter. So we spent some time comparing this. So I'm also going to talk about this comparative work. So how do you compare the two Flickermeters? It's important to bear in mind that the Flickermeter is designed to the original voltage-based Flickermeter is designed to have the voltage fluctuations under control. Since its publication, the Flickermeter became a crucial part of the electromagnetic compatibility standards. Most importantly, the series 61000. Most home appliances are bound to not produce or to have the current consumption patterns such that they don't produce serious flicker. at home when you turn them on, but also big facilities like factories are bound not to produce significant flicker to keep the PST under control. Okay, so it's important to bear in mind that when you compare flicker meters, you have to take into account that it's part of standards that cover a vast area of expertise, and we did a comparative analysis on appliances in laboratory conditions, and then we had the original and also the proposed Flickermeter implemented in field measurement devices. So we did a lot of field data measurements. And then, well, of course, finally, when you have two flicker meters and you are not unsure which one is correct and which one better predicts the human perception of flicker, then the best idea is to let the humans decide, right? So we need to do experiments with human observers, and it's not easy to design experiments with human observers so that you would have like that the results would be strongly in favor of one or the other flicker meter. So this is a comparative work of the simulations of the algorithm with synthetic waveforms. In the original standards, there are a few calibration waveforms of voltage. One of them I showed you earlier. So in total there are 7 of them, and they all should produce PST equal to 1. And this is a comparison of the original flicker meter, and the red one is the proposed one. So you see that there is a small difference, but it's not a crucial one. And then this picture shows sensitivity analysis of the flicker meters. So this means how much voltage modulation do you need to reach PST equal to 1? We tried several modulation shapes, rectangular, sinusoidal, triangle. So you can see that for rectangular changes, which model like switching on and off of a boiler, heater, or large resistive load, you can see that the difference is not that big, but for sinusoidal modulation at low frequencies, but the difference is quite big, and the same also for the triangular modulation. But anyway, these are just synthetic waveforms. I'm not sure how often they appear in real world. So these are data coming from laboratory measurements. We had several appliances that you normally use at home. This is you've seen this picture earlier. This is how they were connected. So you have either a voltage source and then a reference impedance, which is a very specified impedance in the standard. And then there was the load under test, and then we measured the voltage and evaluated the flicker. So you can see that sometimes the difference is not that big, and sometimes the difference is large. The largest difference was air conditioner. And we were interested why was that, and we found out that the largest difference is for big events that happens only one in a few minutes. So in this case, it was the starting of the compressor in the air conditioning device. So this happens. It happened maybe 2 times in 10 minutes, and it was a big voltage dip, a really serious one. So that was a big difference between the 2 flicker values. And then we placed the 2 flicker meters in field at 4 locations, and in total there were for several weeks gathering data. In fact, they were discarding the voltage waveforms themselves. We're just recording the PST and the PLT. So this is a fragment of data. You can see that it was just 2 days from one of the locations. 2 locations were in Germany and 2 were in Czechia. And you can see that the original Flickermeter produces a lot of variation. It reacts to the the voltage modulation quite a lot. On the other hand, the new Flickermeter is more stable, is less prone to making peaks, and it is also almost always smaller value. And well, I made a short summary here also. So this is a comparison of the on the x-side the original PST, and on the ordinate is the PST from the proposed algorithm. So you can see that like really always the proposed algorithm results in smaller values. But this is a CDF, relative distribution function of the ratio between the two PSTs. And you can see that 95% of the time the new PST will be smaller. This is a very interesting finding. This means that if the new Flickermeter was adopted, it would be the same, or it would virtually relax the standards, the limits. So the true voltage modulation could be a little higher because the PST calculated would be a little bit smaller. So to reach PST1, we would need a larger voltage modulation and relaxing the standard a little bit. So maybe the manufacturers of home appliances will be happy about this and will save money. This is another update proposed recently in 2019. This is I'm not going to spend too much time on this one. Just to tell you that there are multiple ideas how to calculate flickermetry. So it's a light-based flickermeter. It does not contain a lamp model, and it takes a different approach to defining the waving function. It starts with impulse response of a human retina in the eye. So according to some research, it seems that the impulse response is a combination of these two waveforms, and you can make two filters based on these responses, and then you combine them. And then also plot 5 is very simplified. You just take the 98th percentile of the signal once per 10 minutes, and that's it. I think that it is a very interesting idea, but I'm not aware that it would be tested in some other laboratory other than where it was published. So there is the space for new research comparing maybe this one Flickermeter. Okay, I won't bother you with many details about this metric. So we are getting to the end of this presentation. So in summary, the original voltage-based Flickermeter. I have to say that it's a very useful concept, and it's based on a very rigorous data and body of research. The original data were replicated in several laboratories around the world in many countries. But it needs updating because the conditions in the grid have changed, and so the lamps have changed. So the idea is to split the lamp model and the observer model. And also, I'm aware that in a power quality measurement field, there is a discussion that maybe the very slow voltage changes or singular events, as I said, like the air conditioning device, they could not be regarded as flicker, but rather they would rename them to a different phenomena called rapid voltage changes. Who knows what will happen in the following years. Then with the Luminous Flickermeter, the sensitivity curve might need to be updated to spectra that are coming from LEDs. As I said, warm white, cool white LEDs. The spectrum is very different from the incandescent lamp. Then maybe we could adapt the Luminous Flickermeter to different luminance levels, not only office lighting, but maybe also public lighting, mesopic vision. and then verify or check that the block 5 is well defined. Probably it is, but it was only based on arc furnace data as far as I know. So in order to arrive to the final PST value, we can have several algorithms, and these need to be compared using human observers. And as I said, it's a little complicated to design the experiment correctly to arrive to sensible data. And then finally, we can have a totally new Flickermeter concept, like metric that would reflect the stroboscopic effect visibility. So there already is one. It's called the stroboscopic effect visibility measure, but it is defined in a frequency domain. And frequency domain means that you have some assumption on periodicity of the signal, and this restricts you really to laboratory conditions. But if you want to measure in field, you want to go to a factory and make a measurement about the flicker there, it's much better to do this in time domain. And I'm not aware of any way how we could calculate the stroboscopic effect visibility measure in time domain. So it might be interesting to try to formulate this algorithm as well. So this is all from my side. Thank you for your attention. These are a few names of my colleagues, which I would especially like to thank to, which will help me with the comparative task of the 2 Flickermeters, and also enabled me to get a lot of knowledge about the Flickermeter, which I passed out onto you, hopefully. So if you have some questions, then I'll be happy to answer them for you.